Okay, let's continue with the second talk of today. It's my pleasure to introduce Yuzuru Sato from Hokkaido University, and he will talk about noise-induced order in high dimensions.
Thank you for introductions. Thank you for giving me opportunity to give a talk here. So I am working on noise-induced phenomena in random dynamical systems, mainly data analysis, modeling, numerical analysis. So this talk will be nonlinear physics style talk. Okay, so these are typical or representative example of random dynamical systems and stochastic nonlinear phenomena. This one is random logistic map with additive uniform noise. And then this one is called the stochastic Lorentz equation, the standard Lorentz equation and multiplicative noise, right, in SDE. So I I'm interested in some phenomena of bifurcation, stability analysis, like more complicated systems in basically, numerical computing. So my talk will be about this first part is review for noise-induced phenomena. A lot of noise-induced phenomena studied in physics, statistical mechanics. So I particularly explain this noise-induced chaos and noise-induced order. What's these phenomena? And second one, I will show you some results about multiple noise-induced transitions with some computer-assisted proofs. This one has some rigorous mathematical results. And the third one is recent observation in numerical experiment. Noise-induced order in high dimensions. It's new phenomena, as far as I know. Right, so I am interested in noise effect for dynamical systems. So I will talk about what is noise and chaotic dynamics. So we start with, I'm working on this time series analysis. So that I like to start with this time series, this data. This n is time, and x and y are observables, some physical quantity, one dimension, and then z looks irregular. Power spectrum has broadband. But there are very simple tricks called return plots. We replot of this data with this delay coordinate. Then x and y, this visualization shows x and y are very different. So this structure is just the data itself. We just change the representation of the data. And in this case, we can say that this time series, this dynamics is deterministic chaos. And then in this case, we don't have no causal structure. So it's stochastic randomness or very high dimensional system. We cannot extract low dimensional causality from this time series data. Right, in some sense, we observe irregular dynamics. And then if we can find small generator, then these dynamics can be chaotic. This is other definition of chaotic systems, I think. But this pedagogical example doesn't work for real experimental data. We never observe this clear, completely one-dimensional structure or completely random. Typically, we observe this kind of vague data. So this data is well-known dripping faucet experiment done by Robert Shaw. He measured interdroplet intervals. We have this kind of very simple experimental equipment. And then he measured this interval of one droplet to another. And we have a time series of this interval time. So Tn plus 1, we have return plot, we have this structure. Right? So this is actual data which have been done by them. Right, so this is of course, this physical experiment. We have some error, observation error or some mechanical errors. So we can approximate this structure for unimodal map. Then we define this F. So this is a modeling based on return plot. And we have a dynamical system model, deterministic. And then do bifurcation analysis or stability analysis and so on. So the other approach can be by using same data, but in this view. And then we have this mesh and counter. We create histogram. So this can be a very simple approximation of Markovian transition matrix, or in the limit, this transfer operator. So we can discuss about station distribution, decay of correlation, relaxation time, or something like that by using this modeling. The phenomena is same, but the analysis is different. And the third one, which I'd like to talk, is we set random dynamical systems, meaning that we have some deterministic part, but we also include random variables in equations. In this case, it's random map. The noise here, Xi n, random variable is depending on the position. We have some fluctuation here, but essential dynamics is this red line. So this is random dynamical system modeling, the other interpretation than this dynamical system modeling or stochastic process modeling, ergodic theoretic modeling. Right, but of course in the real phenomena, this phenomena is not one-dimensional, of course. This is fluids. This is many very, very high-dimensional dynamical systems. If we say this fluids, this is actually computation for this real fluid motion. This part is liquid, this part is air. And then we form, by changing this flow rate, we form this interface to have one droplet, and then eventually this droplet. So even one droplet includes a turbulent structure. So one droplet has big spatial-temporal chaos. But we skip or coarse-grain this entire system and just observe this droplet interval. So in this way, we have this, but actually underlying structure includes this intrinsic noise from this turbulence and the extrinsic noise from experiment or some mechanical noise, observational noise, control error. And then maybe this droplet interval has some deterministic causality. Then we have essential dynamics. These three factors interact with each other. And then as a result, we have this data. This is a precise interpretation. So noise here is actually different from randomness. Noise is a relative concept, physical concept. One interpretation, one definition of noise is uncertain perturbation from other spatial or time scales, other scales. That's a typical definition of noise. So noise is relative. Everything can be noise. We regard it as noise. Right. I will give you one particular example for this experimental setting. So this is, again, very complicated phenomenon. Surface switching in rotating fluid, free surface, rotating, Reynolds number very large. And this surface deform without changing these parameters or set, Reynolds numbers. They observe this slow motion of surface, actually only surface height, it's up and down, and also this fast motion of rotating fluid, this fluid's turbulence. This white part shows the turbulence. Clean, black, it's laminar. Right? So we have two scale time series in this way. This is a time series from real experiment. For the slow motion of center of surface, based on this data, we have this return plot. Then we may have this kind of mapping, one-dimensional mapping. And then from fast motion of rotating fluid. So this is too fast. So that we can measure the strength of the turbulence, disturbance. So this can be modeled by this way. So Xi n is white Gaussian, and epsilon, the noise amplitude or variance, is measured based on this time series, meaning that we model this random variable depending on position. Sorry.
May I ask a question?
Yes.
So you also have, as we have, noise which is position dependent. The variance of the noise depends on position in phase space.
Yes, this is.
But I don't understand. Your side, you have it's observational measure of the variance, right? What you showed.
Yes, yes. This is strength
So
of
that's
variance.
experimental.
Yes. And then this function is just fitting.
But that
by
is a fit
sigmoid.
of the experiment.
Yes.
It's very theoretical model.
No, this is just fitting.
Fit of experiment.
Fit from experimental data. And Xi n is Gaussian like us. Very strong assumption. Underlying turbulence. Yeah. Right. So, yes, this Professor Stefano shows this type of model for financial dynamics, so that I decide I talk this also. So this is typical random dynamical system modelings, and we say some small things, phenomenology. They observed these three states of the surface. They actually did more precise, analysis, not only the height. The shape is different, and they define three states, flat rotation, regular oscillation, laminar turbulent transition, LTS, RO, FR. So these three states switch each other. This is experimental studies, and they don't have model. And Navier-Stokes equation doesn't work because this boundary condition is too complicated. So, but we could have this kind of data-based model, actually just random return plot, have this nice small random map, and do this bifurcation analysis and phase diagram, and regenerate this experimental data. So this has three objects: two unstable fixed point and one stable limit cycle. This M0, M1, M2 corresponding to the observed phenomenological state, this laminar turbulent LTS FR RO. Sorry, it's difficult. Right, so it's, very coarse-grained phenomenology, but better than nothing. They did only experimental work and then no theoretical, no analytical work. So they liked this very much. Right, in this way, we could use this random map, random dynamical system model for rather high-dimensional phenomena. Right, so in this way, I meet this random dynamical system theory and studied mathematics very hard. But formalization is given this way, basically. So model of deterministic dynamics, model of noise, and this affect one way. State space is given by omega times x, but we are interested in behavior in x. We are not interested in model of noise. It's given, or like assume we know the model or input sequence omega. Right, so this is a typical model, one-dimensional additive noise random dynamics. For this kind of system, we could define attractor and its stability. It's called random attractor as a function of omega. Or random, this is statistics, random Lyapunov exponent, lambda, also a function of omega and sometimes x. Right, so this, if omega, we fix omega, we have some particular attractor and Lyapunov exponent. But if omega is a random variable, attractor and Lyapunov exponent itself is random variable. The statistics is random variable. It's like meta structure. But in nice case, this Lyapunov exponent converges to one fixed value, and we can use that. And to discuss average stability of random attractor. Okay, so example, clear example. is given by Langevin equation, linear Langevin equation. This way, WT is a linear process, and it's linear, lambda sigma positive. Interpretation as dynamical systems is given like, this is SDE and usually not discussed in this way, but we interpret this random attractor is random point attractor depending on omega, noise realization. And the stationary distribution is given by Gaussian. And the Lyapunov exponent is constant, negative. So this is an interpretation. It's completely solvable random dynamical systems. But we could extend this to the high-dimensional case. For example, this drift term can be replaced by standard Lorentz equation. And we could put this multiplicative noise term. It's created by this climate dynamics group. So it's called the stochastic Lorentz system, and we can have a strange attractor, chaotic attractor. It's called a random strange attractor in mathematics, and the stochastic chaos in physics as phenomenon. So definition of this chaotic attractor is similar to the deterministic case. So in random case, stable attractor, station distribution, and positive top Lyapunov exponent. This is so far like temporary definition. And this attractor is called pullback attractor. We have to look at all possible dynamics for this SDE or random dynamical system, so that we have to draw all possible orbit. And this is time t snapshot of all possible orbit. This dark area, we have many orbit. The gray area, we have some orbit. White area, we don't have orbit in this experiment. This should be done for all possible noise realization and all initial conditions. And we need to observe all of them. In this case, one orbit is fine, but this case, its behavior depends on the input. I mean, the noise realization. So we have to analyze this all. Okay. Then one nice application is so-called noise-induced phenomena, studies on noise-induced phenomena. So this is studied like 1980s from early chaos studies. So we have deterministic dynamics and some nonlinear phenomena. Sometimes if we add noise, the behavior, phenomena qualitatively change compared with deterministic dynamics. So this kind of transition is extensively studied from 1980s. Most well-known one, this 1D, 2D, 3D is like a dimension of deterministic part. The stochastic resonance is probably most well-known noise-induced phenomena. It's starting from a gradient dynamics, and this potential barrier is moving in some period. And then if we add optimal noise, this internal dynamics time scale is matching to external dynamics, external force. And the second one is called noise-induced synchronization. This is from oscillatory dynamics studies, coupled oscillators, Kuramoto theories. So they found that this synchronization in uncoupled many oscillators, having perturbed by common perturbation, common noise. Uncoupled N oscillator perturbed by common noise, synchronized. It's called noise-induced synchronization. And the third one is like, this is also old, like early chaos study, noise-induced chaos, studied by nonlinear physics peoples to study what is chaos in terms of physics or something. So this is caused by chaotic saddles interact with noise. So this is like underlying mathematical structure to have this noise-induced phenomenon. So in this way, at least these three, there are many more studies, many, like zoo. But by using random dynamical system theory, we can analyze all of them in unified framework. So synchronization is random point attractor. Stochastic resonance, random periodic attractor. Noise-induced chaos is random strange attractors. And noise-induced order is actually window phenomena in random dynamical systems in my interpretations. This phenomenon is like we have chaotic dynamics. We add small noise, chaos disappear, we observe order. So the opposite phenomenon than to this noise-induced chaos. And we also have intermittency. This intermittency is proper intermittency, infinite ergodic, non-stationary intermittency, like Pomomone-Beer, but this critical exponent is different from the deterministic intermittency. So this kind of categorization is possible with random dynamical system theory. This is the starting point of my studies, and these are all studied in different area and different method. But we can just talk about bifurcation in random dynamical systems, stability in random dynamical systems, to characterize this well-known noise-induced phenomenon. Right, so I will explain some noise-induced chaos and noise-induced order, these two particularly this time, because it's related to the result I present. So noise-induced chaos is given, occur in this model with logistic map plus relatively uniform noise. The motivation is period 3 logistic map potentially chaotic. Which is interested in this chaos, unobservable chaos exists when we measure or perturb the system. So the answer is yes. And we have relatively small noise. This is bifurcation. This axis is fluctuation of noise, fluctuation size, and this is bifurcation. We start with period 3 limit cycle, stable, but with some noise level, these dynamics like support of invariant density explode, and it's all connected, and we observe chaotic behavior, and the Lyapunov experiment becomes positive. So this is quite easily observed in the simple computations. Okay, so the toy model, why this happens, is given by this way. Basically, we have this unstable chaotic set between period 3 limit cycle, and the noise access this unstable chaotic set on control set. Then we observe chaos. And this is like tractable model. This is linear mappings, and probably everybody can see what's happening. In deterministic limit, we have stable limit cycle, but this effective Bayesian size is very small. So if noise size is more than delta or some maybe more delicate value, if we add large noise, we jump out from this effective Bayesian to this chaotic transient region. So we have chaotic transient, region, but come back to limit cycle. But we add noise constantly so that this jump out to chaotic transient. So we almost always observe chaotic transient. So in random dynamical system context, this is random attractor, including this chaotic transient. So we have chaotic behavior and Lyapunov experiment about this slope, log L, log kappa to log L change. Right, so this is like a very intuitive toy model. Right, more non-trivial and realistic noise-induced chaos is known as shear-induced chaos. This is based on the Stewart-Landau oscillator. So, attractor is limit cycle on unit circle, and normal form of Hopf bifurcation, and we just add additive Gaussian noise. Then we observe chaos in some parameter. The stationary distribution, invariant density, is actually surprisingly solvable in this way for this system. It's crater-like distribution. And then if this, with these parameter settings, B 0.8 case and B equal 8 case, we have different attractor. Although the distribution is completely same, identical, because this doesn't include B. So B characterizes sphere of this dynamics. If B is small, we have negative Lyapunov exponent, negative top Lyapunov exponent, and we converge to the point. But if B equal 8, we have large shear, so positive Lyapunov exponent, we have this random strange attractor. The stationary distribution is the same, integrated by this strange attractor or point attractor. Right. This is like half-solvable non-trivial dynamics. Then why this chaos happen? If we have B equal 8, strong B, we have strong shear. This is decomposition of the limit cycle. This is theta direction. This is radius direction. If we add a perturbation, if shear is small, it's just converge, go back to limit cycle. But if you have strong shear with perturbation, some large perturbation, we have this bending, right? So we have stretching and folding structure there. So we have chaotic behavior. So, yes? Sorry?
The equation, can you show the previous slide?
Which one? Go back? Sorry? Previous slide, okay.
Thank you.
Okay. Yeah, this is, include error function, so it's not totally solved, but yes. But we could show positivity of Lyapunov exponent in this case and so on, in different mathematical techniques. Okay, but this one is more non-trivial because in two-dimensional ODE, of course, doesn't include any chaotic elements, but adding noise, we suddenly observe chaos. So two-dimensional SDE, in general, generate a strange attractor. You have to know. So one dimension, safe. Two dimension, already we have strange attractor in SDE. Okay, so this is introduction of noise-induced chaos, and I move to explanation of, noise-induced order. So this one is first motivated by this question, is chemical reaction chaotic? Belousov-Jabotinsky reaction is chaos or not, this discussion. And people have this, again, return plot from this experimental time series and claim there's a chaotic dynamics exist in chemical reactions. Surprising at that time. And this other Matsumoto Tsuda investigated noise-induced phenomena or this BZ reaction, this map. This is a chemical reaction map. And without noise, it's chaotic, right? Lambda, top exponent, Lyapunov exponent positive. And with noise, Lyapunov exponent becomes negative, and the power spectrum shows peak. So with noise, we have peak. And this peak is also non-trivial. This peak is not sharp peak. It's like rounded, meaning that there exist many frequency, periodicity at the same time around here. So non-trivial periodicity emerge when we add noise to chaotic attractor. So this is rather more non-trivial behavior, and this mechanism is still unclear. So I'm working on this, and many people working on this to understand why this happens. I will give you 3 scenarios, which is like hypothesis. So, but I use the word background. Okay, so this BZ map has heterogeneous generating partition. This is numerically computed, non-rigorous partition. And these heterogeneous partitions cause this strange behavior, transition. Diversity of orbits decrease when noise level is larger, because we adding noise, uniform noise, this partition doesn't affect. But this area is completely destroyed, packed to this some noise level partition, meaning that, in other words, we introduce uniform partition by force by adding noise. So this makes chaos disappear. Right, so this noise-induced order is often observed excitable system, chemical reaction, neural dynamics, and biological cell dynamics, which shows this steep part. Excitable dynamics has this steep and flat part, typically. So this structure introduced this heterogeneous partition in general. So this is consistent to the experimental observation. So this noise-induced chaos, noise-induced order is also observed in chemical reaction experiments. So it's really exists. So the second one is similar to noise-induced chaos scenario. So this chaotic attractor includes, or like unstable periodic orbit exists near the chaotic attractor. Adding noise, the frequency to visit such unstable periodic orbit increase. So in noise-induced chaos case, we have a limit cycle, but this unstable chaotic set on control set, and adding noise, the chaos observed. Maybe just to directly interpret this noise-induced order, we have a chaotic attractor, and some UPO is weakly stabilized. It's not stabilized, but it's frequently visited, so it looks like stabilized. So this is one explanation, classical explanation. Right, so original system doesn't change, but adding noise or measurement, try to measure that system. So measurement requires noise. We have to add noise to measure some phenomena. So that in that case, sometimes this density, stationary density, drastically change and observe the phenomena qualitatively different. So this is based on such physical intuition. Okay, so the third one is more recent interpretations. It's related to statistical periodicity. So this is based on the spectral analysis of transfer operator. So typically we have, if we add noise for dynamical systems, we have this kind of spectrum, which is like this is one, and this is this red circle eigenvalue is close to one, but not one, very close to one. So the very small spectral gap. In that case, we have very slow oscillatory relaxation to stationary state, so that this is a relaxation process in numerics of sample measure. This period 3 in this case. And if we have other like 5 eigenvalues here, we have period 6. And many periods observed, typically in random dynamical systems. So this can be the origin of noise-induced order. Chaotic dynamics, adding noise, we have this extreme structure, extreme resonance. This type of resonance induces finite time oscillation. This is kind of regularity. So this is the third scenario. But basically, they are all, of course, numerical or physical analysis. So no mathematical result exists as for mechanics. Okay, so this is a summary of, I have 10 minutes or so. Okay, so noise-induced chaos and noise-induced order. This Lyapunov exponent negative to positive, positive to negative. And characteristic frequency in noise-induced chaos case disappear, order case appears, and so on. So we found rather new phenomena, extension of this view. It's multiple noise-induced transitions on this map. It's called, we named this modified Lasso-Tamaki map. Adding noise, additive noise, we observe multiple transitions. We start with chaos. Adding noise, it's Lyapunov experiment negative first, and increasing noise level, we observe chaos again, lambda positive. And then increasing noise, we observe negative Lyapunov exponent. This kind of multiple transition is also typical because this map has a lot of windows. So this can be, this transition can be many, happens many times in general. Okay. So for this, we did computer-assisted proof of existence of these multiple transitions. So computing Lyapunov exponent, not by time average, this is like a physicist approach, but this ensemble average. So we approximate this stationary distribution, invariant density. So in deterministic case, we have a very bad stationary density, but adding noise, these singularity disappear. So it's easy density. So that this is tractable. Very tractable. This is not archived. This is already published. So this can be old slides. Then we can approximate this stationary density by using Ulam discretization based on delta mesh. So this is the operators. And then we can have this probability vector. And based on this vector, we compute rigorous bound of Lyapunov exponent in this way. This red is upper bound, blue is lower bound. And if upper bound is negative, this real value can be negative. So in this way, we show this negativity and positivity of Lyapunov exponent with some mathematical observation. And this statement is theorems, at least mathematical fact. So we have this multiple transition, at least mathematically. There's no experiment, but this multiple transition, which is very counterintuitive to me, is really exist. Okay, so I will show you the recent other numerical experiment. Just found this phenomena. So I tried to introduce this noise-induced transition concept to higher dimensional dynamics. I take this generalized n map, n-dimensional map, but n equal to its n map, and it's a delayed logistic map. And the chaotic attractor is like this when n equals 3, and we have two positive Lyapunov exponent. And if we set n equals 6, 6-dimensional delayed n map, delayed times 6, then we have this numerical experimental result of Lyapunov spectrum. Epsilon is noise level, and this epsilon 0, we have 4 positive Lyapunov exponent. Increasing the noise, we have 3 positive Lyapunov exponent, and then 4 and 5. So this Lyapunov spectrum change is found numerically. And the computation looks very stable, so it's very natural result for me, at least as a numerical experiment. Right. So we also found like counterintuitive phenomena. So this is without noise, attractor projected to 3D space. This is with noise in also same 3D space projected. Lyapunov exponent 4 to 5 positive Lyapunov exponent. We have this global stretching and folding structure newly. So this contributes new positive Lyapunov exponent, possibly. And this is invariant density. And this red one is period 2 UPO in deterministic case. In deterministic case, this UPO doesn't affect this attractor. But with noise, we have a peak near this unstable periodic orbits. So this unstable periodic orbits attracts many orbits, and then density becomes larger. So this is strange because also, okay, so we also measure power spectrum is, if we have time series, first things to do. So we observe this frequency 1/2 is the maximum. So it's meaning that period 2. So we have this characteristic period 2 observed. However, we have more positively appropriate exponent. So this looks noise-induced chaos, but this is a property of noise-induced order. Adding noise, we increase chaoticity in this sense, but we observe ordered behavior. So this heterogeneous or coexistence of both transition is possible in this high-dimensional dynamics. So simple noise-induced order or noise-induced chaos discussion doesn't work, actually, even in this simple high-dimensional dynamics. So we have to think carefully, or maybe we need a new measure. So we also observe other phenomena. This smaller noise, number of positively appropriate exponents decrease, like noise-induced order. However, generating Kolmogorov-Sinai entropy increase. It's possible in high dimension. Right? This Kolmogorov-Sinai entropy estimated by sum of positively appropriate exponent. And in this case, number of positively appropriate exponent increase, but we observe some ordered behavior. Characteristic frequency, period 2 emerge with stronger chaoticity. Right, so this is the last slide. This is summary, like random dynamical system approach. Like nonlinear physics, we have a dynamical system approach. We could do the same things with this stochastic dynamics and discuss about bifurcation or stability. Multiple noise-induced transition, this is newly known, exists, and this is even proved of mathematical computer-assisted proof. And this heterogeneous noise-induced order in high dimension is possible. Okay, so this is the end of my talk.